we will go ahead and post this or make this available to people. So, so please, if you have any concerns about being recorded, perhaps you can just use the chat to communicate with us, and we will go ahead and read your comments and your responses to some of the questions. So good morning, my name is Leanne Ketterlin-Geller. Hopefully most of you heard our previous introduction, but I'm joined by three other colleagues, Deepa Srikantai, Wendy Ralangita, and Norma Evans. And we are talking about instructional strategies for early grade mathematics. And in the chat, I've put the link to this document. This is a document that we will be referencing throughout the presentation this morning. And I'm also going to share with you the authors of this document. This was truly an multi-institutional collaboration and collaborative effort to bring together evidence-based practices to support students' mathematics proficiency and students' development of productive math habits. So I'm actually going to just switch quickly to the presentation. We've lost a little bit of time this morning, so I want to make sure that we catch up and we have enough time for people to engage. So I'm going to begin the presentations. It'll just take me a second to get this up. Here we go. Hopefully you can all still see the screen.
Yes.
Oh, great.
Visible.
Okay, to kick off this morning, Wendy and I will be talking about developmental progressions and formal and informal connections. And I'm going to start by talking about developmental progressions, and this will continue through our discussion today. So let me see if I can, oops, okay. So developmental progressions are research-based pathways that represent how students increase in the sophistication of their understanding across concepts and within concepts. And this is an example of a developmental progression. This happens to be for numeration. And as you can see, if you follow the arrows along here, this begins with students' ability to state, recite, or recite number words in a stable sequence, and it progresses through a series of skills and knowledge that ultimately ends with the student's ability to accurately count collections of 20. So as you can see from this, there's a progression in the complexity of the skills or the knowledge that students are using, and it builds on prior knowledge. Each one of these successive steps along this pathway builds on prior knowledge and then culminates in some sort of terminal skill. When we say that it builds within and across concepts, clearly this is not where we want this skill to end, so this is going to continue, but this is a natural ending point for this particular developmental progression. But we also know that there's a variety of different skills and knowledge that students are accumulating as they're working through this particular developmental progression. So we can think of this as a network or a lattice of different skills that are progressing. Some of them may be progressing more rapidly than others, and some may be progressing a little bit more slowly. It is also important to note that this is not a fixed sequence. Every student doesn't progress through this sequence in exactly the same way or in equal intervals, but this is based on the accumulation of research and how students learn, and it's useful in a number of ways. So that's what we're going to talk a little bit about now, and the focus of this discussion here is we want to talk about how these progressions are important in instruction. And these can help serve as a pathway or sequencing pathway for teachers as they're designing instruction. Also helps teachers understand students' thinking and students what might be some plausible students' misconceptions or plausible ways in which they're going to be developing their understanding along this continuum. So as teachers understand where students are located within this progression, they can use that information to better understand what background knowledge or prior knowledge the student has access to or has already developed understanding, and where they're going to move toward next in their learning. And teachers can use this to sequence their instruction. So as an example, if we take this developmental pathway, and as you can see on this sequence, one of these locations says accurately count any collection up to 5. So if we know that a student is at this point where they're accurately counting collections up to 5, we may have identified that the student is at that point by doing a series of assessments or looking at their prior knowledge. So if we listen to students or collect students' work samples, listen to their thinking in an instruction, or use an assessment that can help us better understand where students are placed, we can note that a student who is able to accurately count any collection up to 5 should have these skills and knowledge as their background knowledge. And so we can build upon those knowledge and skills as we design our future learning. So teachers can use this to identify where they should go next in their instruction and how they can prime that background knowledge, or how they can take advantage of that background knowledge or prior knowledge that students have to move their thinking forward. So we're going to take just a minute and hopefully give you a chance in the chat to share some ideas about how knowing this child's location can support instructional decision making. What are some things that you've seen in practice, or some things in which that we haven't talked about that you can see using this information? We'll take just a minute to pause while people provide some thoughts. If no one would like to chat, maybe someone wants to unmute their microphone and jump in.
I guess, yeah, and one question that I had was, this is Luis, whether, I guess, I don't know enough about early, math, but whether kind of calling it something like instructional decision making, that phrase sounds rather formal, and it seems to me that, from watching my grandkids learn and my kids, again, given that I'm not an expert, a lot of this seemed to me closer to play, or to kind of instructional play. And yeah, I guess I'm more curious around the how you can approach this as something playful, to some degree. I guess one question is, where would this be taking place? Okay, for grade 1.
Okay, so great question and point of jumping in. This does, so you're right, the word instructional decision making is a formal recognition of how teachers might use this. But this is also something, if we were to use this in a play setting, where we would still want to look at, for example, being able to accurately count collections up to 5, where the marker is now, that's something then, if we were looking at a play setting, that we would then move towards the next phase, which is recognizing the irrelevance of the order of objects, which is the next pathway over, or the next step in the pathway, that we could then look at, asking students if we had, or asking children if we had a collection, or if we had a collection of asking about how does it matter if I take these 5, or what about these 5 or these 5? And so kind of moving through different ways of making 5 within a collection and asking them to identify if it matters the order of those objects when you're then counting them. And then that could move into what if I bring in 6, or moving into increasing the size of that collection, so that then we're moving to the next kind of milestone, which is accurately counting collections to 10. So it doesn't have to be in a formal setting of instructional decision making. It can also be as you're interacting individually with children, and in a play setting, or even in more small group instruction. But it's something that you could use this sequence and use this development of sequence to help structure the learning in the learning environment, so that you are not jumping too far ahead more quickly than what the child may be ready or able to do at that time, but you're also not kind of continuing to step back on the progression as well, because we do want to continue to make sure that we're making forward progress for students. So I'm going to go ahead and move to the next section, which is kind of how we would think about, and specifically in instructional settings, as opposed to play settings, which I think this certainly can be bridged between those two. And I think as we move into the next presentation on formal and informal, this is something we can circle back to. We talked about how interpreting students' performance if we're thinking about the developmental progression, can help teachers understand students' prior knowledge and future learning, so that they can sequence instruction. But we think about the pedagogical responses that teachers might make as they're understanding that progression, and where students are performing along that progression. Teachers can use this information to design activities that increase in complexity along the developmental progression, and again, are moving at an appropriate pace. Teachers can also use this information to differentiate instruction based on the student's relative location. So one of the challenges that we often find with differentiating instruction is maybe not necessarily teachers struggling a little bit with what to differentiate, not necessarily just the process of differentiating, but how to differentiate the content. And using developmental progressions can provide a framework for how to differentiate the content of instruction. And then using that to organize instructional groups, either that focus on different activities, or are located at different places within that developmental progression, so that all students are continuing to work toward the increased sophistication, or increased levels of sophistication within math concepts, but they're moving at their appropriate pace. So we're going to come back to this, the idea of developmental progressions, as we continue our discussion today. But for the sake of time, I'm going to pause here and move towards the formal connections between the formal and informal mathematics. And I'm going to turn over control to Wendy. So just give me a second to stop sharing my screen and to change the presenter to Wendy. Okay, Wendy, you should have access to that now.
Okay, let's see. Can you hear me and see the presentation?
Yes.
Great. Okay, so shifting to making connections between formal and informal mathematics, starting with what these are. When we talk about informal mathematics, this relies on the idea that humans are born with an innate sense of quantity, as well as an interest and sense of patterning, both of which develop as they interact with the world around them. As children encounter different problems, they develop strategies to solve them, which may work, but are often problem and context specific. I was thinking of this last night when I was cooking dinner, making rice, and I remembered the the strategy that I learned in Namibia, where if the rice goes up to the first joint in your finger, the water goes up to the second joint. And that's a really excellent strategy for estimating the amount of rice and water you need, but it is not transferable to any other context. So that's jumped to my mind last night when I was thinking about this. And there's a lot of different areas in which children are developing their informal mathematical thinking. But when it comes to formal mathematics in school, where mathematics, and that's what we mean by formal mathematics, it's the mathematics you typically learn in school, which is symbolic. Now you learn the numbers, the number shapes, the equal sign, the addition sign, all of those things, and they're generalizable. So where you would have this very, very specific estimation and measurement strategy for cooking rice, in math class in school, you want to have rules and approaches and strategies that can be generalizable to any similar problem. So this is another way of looking at the difference between informal mathematics and formal mathematics every day through being learned through school, the generalizability. And I think the examples again give a nice illustration or picture of how that works. So in many places, children may be going to the market to do some shopping, but they may be always using the same notes. Maybe they're typically using money that is in 50s, you know, and so they get good at calculating change in 50s. But that doesn't mean that they would, if you switch up the numbers, they would still be able to figure out the change. Whereas in school, you want to learn methods for calculating the difference or the change, no matter what those two numbers are. So that gives it a little bit more of the picture, the difference between the two. And why is this important? In some ways it links to the general idea that you want to build on students' prior knowledge. Students come in with a lot of this innate sense of quantity and patterns, but they may not be able to generalize from them unless you help them. The problems that they face in the real world are authentic, whereas typically, traditionally, some of the problems that they may be given in math may seem artificial or not to have meaning. I think of the classic problem of this, you know, that one train is traveling at X miles an hour and the other train is traveling at Y miles an hour, and how long it will take them. And a lot of us laugh at that because we cannot picture ever actually having to solve that problem. All you have to do is look at a timetable for the train. So so this is you know a problem that a lot of children face. They have this understanding of quantity and patterns and mathematical thinking from the informal outside world, but then they see no connection to the school math and end up very challenged by that. So drawing connections between the two would build on the children's prior learning. It can enhance understanding, because if you can start to help them see that what they were doing at home or at the market when they were getting change is the same thing that you're trying to work on in the classroom, and you can build from what they already know. And it can also help them see that generalizable strategy that they're learning in math could then actually go back and be applied in the real world. So how can they be used in the classroom? So one way is by bridging, where the teacher discusses with the children and helps them see how a problem or concept that they're working on in school is linked to an out of school math problem or an out of school strategy. And usually one of the first steps is to think about what is the math, what is the mathematical thinking that children are doing outside of school. So I just want to take a minute and ask you to just jot down an idea or two in the chat window as to what are some of the everyday activities that you think children may do, you may have seen your own children doing, that involve mathematical thinking. So I invite you to just jot a quick thing down in the chat just to share some ideas. Change making, yeah, exactly. A lot of kids go to the market and have to learn whether or not they're getting the right change or bringing the right change back to the parents. Any other ideas? Passage of time. Yeah, it's funny because one of the things I was thinking of that example, Louise, and that's certainly true. I was also thinking of a lot of places where people don't look at the clock, but the passage of time is through the where the sun is in the sky. And that there's kind of thinking of angles too. They would hold their arm up to point at where the sun is going to be at the time we're supposed to meet. Distributing items equally, exactly like in fair sharing. So you've actually and directionality, good, exactly. And so you've already, if I can get back, let's see. You've already mentioned, this is not forwarding now, let's see. So I got, okay, here we go. So you already mentioned most of the examples that I had put down, which is fair sharing. I already mentioned about the rice cooking and can involve a lot of measurement and estimation without realizing you're doing it, and simple purchases at the market, and then some other examples that you guys share: directionality, time, etc. And so then another way, and so by drawing on these things, the teacher can help the students to see they're already doing some math, but maybe we can move it a step further and start to generalize from that. And then another thing the teacher can be doing is using problems that are connected to everyday math. So we have three different problems here, each of which is the same mathematical concept. It's the same problem, but it's asked in three different ways. So I want you to just take a minute or two and read through these problems and put in the chat, which of these do you think is easiest for children to solve? Yeah, so it is likely that the third one is going to be the easiest to solve. The first one is kind of a very typical classic word problem. It's decontextualized. It's rather abstract. Yeah, thank you. If they have an auntie, yes, that's true. So the second one, well, it's more connected to real life. The question is it something that a child may have experienced? Does a child find themselves in a situation where they would have to figure out who sits at how many tables do you need? How many are sitting at each table? Maybe if they were organizing their wedding, perhaps, but that would be a little older. That's less likely to be something they're familiar with, whereas sharing candy is more likely to be something that they're familiar with. And then, of course, you would want to move on from there. You don't want to be that's the only scenario that they can solve the problem. But if you can bring that into the classroom, then you can move children on to perhaps more abstract problems. You can change the numbers. You can eventually get at looking at more abstract problems in the same way. Let's see. Okay, so now that's sort of the summary of, and I do hope that this also links back to, it's clear how this links back to Louise's comment about learning through play, where the teacher, a lot of the things that our children are doing when they're playing are mathematical, but they will need somebody to help them generalize some of the strategies they're learning, some of the patterns they're seeing. How is this generalizable? How is it linked to symbols? And so that's where understanding where children are and where they need to go, and how the informal mathematics they're doing when they play links to formal mathematics that we want them to be able to develop. So now putting these two instructional strategies together, this is part of a lesson from the Tayari project in Kenya. And what I'm going to ask, this is the kind of thing that you might do when you're working with teachers. You want to develop the understanding of developmental progressions. You want them to be thinking about connecting formal and informal mathematics. So this is the kind of conversation you might have with teachers in that respect. And so I'd like you to think of yourself as teachers, or think of your role as teachers, and have a look at this activity or this part of the lesson and answer a couple questions, reflection questions. If you were the teacher, what would you say students have to already know in order to do this activity? And then what linkages does the lesson make with students in formal math? And so take a minute to read through, and then maybe we can share either through the chat or, if you want to unmute and share answers to those questions. So Luis has pointed out that as you're going through the bullets, you're making a bit more abstract. Exactly, and actually, Deepa will be soon presenting about representations and modeling, and this is a good example of that. So what would students have to already know in order to do this activity in terms of their developmental progression? What mathematical understanding do they already have to have? Yeah, exactly. They have to be able to count, or they're not going to be able to work through the problem. And yeah, and the sense of comparison, that is assumed. Exactly, that's something that's assumed, and you're assuming when you give this problem that they realize that 7 is bigger than 3. They know how to count objects. Okay, and I'm sure there's more, but to move on, what linkages does the lesson make with students in formal math? In other words, what are things that children might do or be thinking about outside of school that any part of this lesson builds on? It could be shopkeeping, or even, yeah, exactly, sharing. And this isn't fair sharing here, but it is the idea that if you give some of your whatever you have to somebody else, and of course mangoes, if it's a place that people eat a lot of mangoes, even that will be building on their familiar context as well. Okay, and then if we were to continue with this, we won't go through these additional questions, but just a couple questions. I have a hard time getting, there it is. Just adding a couple additional questions one might ask, discussing this with teachers. Okay, you talked about the developmental progression, that what do they have to know? Then you might ask them to consider, how could you make the activity less difficult? How would you sort of step a child back if they're not quite there on the progression? Or if it's easy for them, what are some things you might do to make it more difficult? Where teachers have to be thinking about, what is the most closest previous step on the developmental progression? What is the next step? So you don't go too far back or jump too far ahead, but it's just right in terms of the progression. And then beyond, what are some of the linkages that the lesson makes with the informal math, could you do a better job of it? Are there any ways that you could strengthen that aspect of the lesson? So some of those are some of the things you might talk through with teachers as you're working on developing these strategies, these skills and these strategies with them. So that is our presentation on developmental progressions and linking informal and formal mathematics. I will turn the presentation back to Leanne, I guess, who will share it with Deepa for the next presentation. Thank you.
Hi, everybody. Good morning, good evening. I hope that you can hear me okay.
Yes, it's okay.
It's okay, great. Okay, so I hope everyone is staying safe and healthy. And today I'm going to be talking, or in this part of the presentation, I'm going to be introducing mathematical models and explanation and justification. So this is a picture of a first grade student attempting to solve addition and subtraction problems. And so in this presentation, we'll be going through mathematical models and explanation and justification to think through how this child could use these strategies to solve these types of problems. And you'll notice that a lot of the pictures are from when I was working at GPE, and Lucy, you may recognize them. First, I'm going to be talking about mathematical models. So mathematical models refers to any type of picture, drawing, or object that represents targeted mathematical ideas. And when mathematical models are actually physical objects, such as counters, they can also be referred to as manipulatives. And manipulatives is a term that you may have heard or used quite a bit in mathematical instruction. So when young children think about, they think about concrete ways, or they think in concrete ways rather, before they think in abstract ways. And this is where, objects such as counters or manipulatives are very helpful, because this carries into their mathematical learning. So children start with concrete materials like counters, and they can use that to model target mathematical ideas. And they can also work with pictorial or drawn models and some other examples, which I'll go through in the presentation. But eventually the goal is to support children and so that they're able to reason with abstract symbols and ideas without any mathematical models of those symbols. So then they'll start to independently think about these ideas on their own. Mathematical models benefit all children, despite, irrespective of their abilities. They also enable children to see abstract mathematical concepts. They allow children to reason concretely with mathematical ideas using physical objects. And the symbols that we use in mathematics, such as addition and subtraction, also then start to become more meaningful for students. So here's an example of a child in India using straws as manipulatives to solve a problem. And I'll go through exactly what this child is doing. The child is creating bundles, so bundles of 10 straws, and I'll go through this example in another slide. So therefore, mathematical models help children grapple better with logic and meaning underlying the symbols, procedures, and rules. And I'll go through a couple of examples of what mathematical models are. So mathematical models, actually I'll just go to the previous slide, 1 second. So mathematical models are anything from base 10 blocks, pattern blocks, geometric figures, dice, fraction pieces. They can also be visual or they can be drawn. And go through this. Next slide, yes, okay. And one example is base 10 blocks. And base 10 blocks are designed to make visible key properties of the base 10 number system. So any materials that feature units such as the small cube, which represents 1, a 10 rod representing 10, 100 block, a square made up of 100 or 10 rods rather, and then you have 1,000 block, which is 10 of the 100 blocks. This is one example. And this is an example of how the base 10 blocks could be used with a place value chart. So putting the ones in the 5 unit cubes in the ones box, and then the tens and the hundreds to illustrate how much they represent. So this is 315. Another example, you saw the child using the straws and creating bundles from the straws. So another example is taking sticks or straws and bundling them together in tens, in a group of 10 rather. And this bundle can also be placed onto a place value chart. So if you have the number 41, for example, oops, sorry. Technology, I escaped out of the presentation. Okay, so for example, in this case, the number is 41 because you have 4 bundles and then you have 1 extra stick. Okay. A number line model is also another great way to teach numbers, addition, subtraction. So a number line model is a drawing or a printed representation that models or shows order and magnitude. It's a great way for a student or a child to be able to develop their number sense. Number lines are also great resources and can be used in different ways. As I mentioned, they can be used to teach children how to count. So for example, we have counters. So this is 1 counter, this is 2, 3, 4. Okay, and you'll also see that the distance between the numbers remains constant. And so that also allows the children to see that between 1 and 2 and between 2 and 3, they're equal. So you can go from 1 to 2, that's 1 unit, 2 to 3, that's 1 unit. You can also use number lines to solve addition problems. So for example, if we're trying to solve 3 plus 4, so we can put a small dot or a counter on 3, and we can move it over 4 units. So then the answer is 7. So then the number line can also be used that way. Number charts are also very useful, and I noticed that number charts are used quite a bit in South and East Asia as opposed to number lines. And they can help students learn numbers, practice skip counting, counting by tens, and addition and subtraction. Manipulatives such as counters can also be used with a number chart. Something's going on with my computer, but manipulatives such as counters can also be used with the number chart to help children, associate how much the magnitude of the number. So like 2 counters can be put on the 2. In this case, the child is pointing to the number 45, and the other children in the group, so they're doing some group work here, they have to basically say what the number is. So they were playing a little game there. A 10 frame is another, also another really great resource for students or children. It's also known as a 2x5 grid. So in this 10 frame, for example, we have 4 green counters and 1 yellow counter. So we can say 4 plus 1 is equal to 5. Or we can also ask a child, how many more yellow counters do you need to make 10? Fraction pieces are also a great way to teach fractions for students. And this is an entire fraction piece, but it's actually cut up into pieces. So for example, if I have 1 piece of illustrating the 1 of a fraction piece, I can show a child how the 1 can be split up into 2. And this is just one example of how fractions can be taught. Pattern blocks also allow children to learn different types of shapes. And they can be either cut out into, from paper, or you can actually have physical blocks, but they're really great for children to understand the number of sides on different shapes and how different shapes, or how they differ from each other, the properties of different shapes. And last but not least, finger counting, as it was discussed in the last presentation, is also a really great way of for children to be able to solve problems. And I've seen children not only use their fingers, but also the lines between their fingers to keep track of numbers and solve problems. So when we're using models, here's some guidance in terms of thinking about how to use models in your lesson. So first, it's important to determine what the math content is of the lesson and what features of the model can be used with the content. And then to plan the lesson out. What will the model be used? What model will be used rather? You know, manipulatives need to have an accurate representation of the concept just to make sure that everything is aligned. How can the model actually bridge the abstract and the numerical representation so that the child learns the concept and then doesn't have to use the model moving forward? And when will the models be used in the lesson, and how much time will be allocated to using the models? Okay, now I'm going to go into explanation and justification. So explanation and justification is important because first, it deepens the understanding for children. It allows children to explain their thinking and justify what solutions that they're coming up with. You know, either they can talk to their teacher saying, 3 plus 4 is equal to 7 because I'm adding 4 fingers to 3 fingers, or they can also discuss it with a peer. It also allows children to better organize and clarify their concepts. And also if they're, become aware if their, answers are correct or not, and, what gaps they may need to fill in order to better explain or understand the concept that they're trying to learn. It also increases motivation. So when teachers ask their students or their children in the class to explain and justify their thinking, the teachers can then communicate that they're also respecting and valuing what the children are learning in the classroom and the children's thinking. And this can help children think about or become more positive in their view of mathematics because the teacher is asking them what their thought process was in solving the problem. And it also, like if they're allowed a chance to discuss with peers, this also creates a very positive energy. So then, they're saying, I'm allowed to not just, it's not that 3 plus 4 is equal to 7 and then I move on, but I can discuss it and talk about it with my peers. And finally, it allows teachers to tailor instruction according to the level of children's understanding. So when teachers, ask students and then listen to children's thinking, they're able to identify what children know, and this ties back to the prior knowledge that was discussed in the previous presentation, and then fill in any gaps in understanding that the children don't have. And it also helps the teacher to understand if the children are using the right vocabulary in their mathematical thinking. So here's some sample questions that the teacher can ask in the classroom when the child is solving a problem. They can ask, how did you get to that answer? How do you know that you got to this answer? What do you notice about, for example, what do you notice about, switching the 3 and the 4? If I have 3 plus 4 equals 7, and if I put 4 plus 3, just as a very simple example, what do you notice? Do you still get the same answer? How is this the same or different from? So how is addition, the same or different from perhaps subtraction? And what else could you have done, to solve that problem? Figured out what what a particular word means, for example. And some other things to consider here is that teachers can also model thinking for the problem. So when they're solving the problem on the board for the first time with the entire class, they can say, I'm thinking through how to solve 3 plus 4 equals 7. So I'm going to get 3 counters to represent 3 and 4 counters to represent 4. And when I put them together, they all add up to 7. Something like that, just to help the children think through, this is how you think through the process of solving a problem. And also teachers can encourage students, that mistakes are an opportunity to learn. So even if you make a mistake, it's okay. So just to encourage the thinking process, and when, if they do make a mistake, think through what their mistake was. Teachers can also provide or have a wait and think period or think time for the students to answer questions. So not, asking a question, how did you get to that answer, and then getting an immediate response, but letting the child think about how they got to that response. And this is also a great time to use pairs or group work to allow students to be able to talk to their peers and exchange ideas about how they solve the problem. And also to, again, use the right vocabulary as they're solving the problem. So therefore, explanation and justification allow children can explain or justify their thinking orally in writing or by using drawings, diagrams, or manipulatives. Right. So just as an example, I think we have time. We have about 5-6 minutes maybe. I wanted to go through this problem. So looking at this child, this is a 3rd grader from Cambodia. I wanted you to take a look at this and see, this is a very good attempt to solving the problem, as you probably all agree. However, think through how mathematical models and explanation and justification could have helped this child better solve, or solve this problem accurately, or think through the problem differently, maybe to get the right answer. And either you can put it in the chat box, or you can also unmute yourself. So I'll give you a little bit of time. I can go back to the previous slide so you can see the problem, but thinking about how we can use mathematical models and explanation and justification to help the student in Cambodia work out this problem. Sorry, I'm having difficulty seeing the chat, so I'm going to minimize my screen. Leanne or Norma, do you see the chat? Any responses yet? I can't access
Yeah,
the chat.
so Ben has said if they were using blocks, they would understand that something was wrong in how they were representing the problem.
Okay, great.
He says since both 54 and 66 are higher than 20, so they would at least realize there's something wrong because there should be much more blocks there.
Yes, that's a good one, yeah.
Luis base 10 blocks. Luis says, wouldn't that take a lot of blocks? Individual, yeah, but base 10 blocks, wouldn't take as many individual blocks.
Yeah, that's another good one. Any other thoughts?
No more chat messages.
Okay.
If they were using bundles, sorry, one more. If they were using bundles, it would be fast to see there's a problem.
Okay, great. So I wasn't sure, I don't know if there are any other thoughts on the problem.
No, that was it.
Great. Okay, that's all great. The bundles and base 10 blocks. Yeah, exactly. To help the child work through the problem, because as you can see, the child has attempted it, it's almost accurate. They're probably just modeling what the teacher had been doing on the board, but forgot to bring the one down. I want to just show you one more slide since we had some time. So just, in terms of, this subtraction problem, 22 minus 7 equals 15, and how we can use bundles and also the place value chart to do this. So the child can put the bundles, in the appropriate places. So that's 7, sorry, got cut off a little bit. But yeah, then the numbers, then associate the numbers with each of the manipulatives, and then solve the problem. All right, so that's all on my side. I'll hand it over to Norma.
Okay.
Thanks, everyone.
All right. Can everyone hear me? No.
Yes, clearly.
Okay, great. Okay. We are a little over our time, but we are going to continue because we're recording this for people who couldn't make it. If you have to drop off, please feel free to do so. Okay. So I'm going to be talking about some of the cross-cutting issues that we addressed in the document that we produced. And hang on, okay. And those include sort of the type of classroom climate that you need to build it in order for these strategies to actually be implemented as intended, and looking as well as some of the language issues around language of instruction, mathematical language or vocabulary, and how different languages communicate mathematical concepts. We're not going to be addressing those directly, just because we don't have enough time, but we put those up there in case after the presentations you wanted to bring any of these issues up. The two that I am going to be looking at are sort of looking at instructional models for mathematics and some elements of teacher professional development in mathematics that are important. So I'm going to start with instructional models, and just a very simple definitions. And instructional models are just clear guidelines on how to best structure learning for a discipline. And two of the critical components of an instructional model is they have to be based on research, both about the theories that we have about learning mathematics, but also some of the evidence-based ways of structuring learning. And those are some of the things that we've been addressing in this presentation and that are addressed in the document. So I'm going to give you two snapshots of instructional models. And as I go through this, I want you to think of what are some of the instructional strategies that you see in this lesson, or how might you label the instructional model that's being used here. So this first one is, whether the learning objective, and it's around a P3, is whether students are able to use the strategy of forming friendly numbers that add to 10 to add numbers. So if this was a P3 class, I might start by putting on the board 97 plus 26 equals. And I might say, that's a really hard addition to do. So I'm going to make some changes to it. And I'm going to change the 26 to 3 plus 23. And then I would ask the students, the question is, can I do that? What have I changed? Can I do this? And is it going to change the answer? And we're going to talk about that. And then I'm going to say, well, I'm going to now add 97 plus 3, which gives me 100. And now all of a sudden I've got 100 plus 23. And we're going to work through that answer. That's a really easy one for us to do. It's 100 plus 23. And then I'm going to talk to the children and say, does this give us the exact same answer as if we added 97 plus 26 using some other ways that we know to add? And then we would test that hypothesis to see if it's the same. And once we come to the conclusion that it gives us the same result, then I would try some other ones together with the children. And you get some examples on the screen. And I would do as many as I need until I get a sense that they're understanding what's happening. And then I might ask them to label, how are we going to name this strategy so that we remember it and we can use it? And then once we have a name, I'm going to ask them to do this on their own with a partner and see if they can use that strategy to find some answers. So if this was a lesson that models an instructional strategy, it's an instructional model, how would you label that model, or what instructional strategies do you see embedded in this lesson? So I'll give you a chance to either use the chat room or just to unmute your microphone and talk about what you've seen here. Okay, I'm not seeing much chatter. So I'm going to move on in case the next one gives you a point of comparison between the first one. Oh, yes, some are, Luis is right, some are much harder than the others, and I do want to put some differences in difficulty as we go along. Okay. All right, I'm going to move on to the next one, which would be a P3 or P4. And what I'm trying to, the learning objective that I'm working to in this lesson is whether children are able to identify numbers that are divisible by 5. Can they recognize the pattern in it? So in this one, I'm going to do it as a task. So where children have the hundreds chart, and I want them to identify which numbers in the hundreds chart, whether each number is divisible without a remainder by 5. So in this lesson, children have a calculator. If it was a low resource country, I would do it without a calculator. And what I want them to do is I want them to color with a partner, color the numbers that are divisible by 5 in green and the numbers that are not divisible by 5 in red. And I want them, once they have worked through that, I'm going to have a discussion with the entire class about what patterns did you notice? And why do these patterns appear? And how might knowing these patterns be useful in the future? So that's a very different instructional model than the first one. So I'm going to give you a few minutes if anyone wants to compare and contrast the differences between these two. So I see a comment that the second one with the 100 charts bridges to abstraction more because children are actually, I'm going to make sure I've got the right one. Louise, are you saying the first one or the second one bridges to abstraction more? Okay. I think what you're reacting to is that children here are actually discovering it on their own, that they are playing around with the concept and they're trying to figure out what the pattern is on their own, so that there's a little bit more engagement, intellectual engagement on the part of the children, where the first one, I'm actually leading them through it. I'm asking them some questions, but I am pointing out the strategy that I want them to actually be able to use. Okay, and I see another comment. The second one is easier since they're coloring in on the chart. They actually have something to do, and they're working through a number of numbers, and they're working with a partner. Yeah, and when they color, they will see the pattern. Yes, it should become evident. But then the question is, why does the pattern appear, and sort of how is knowing this going to be useful? So we have two very, very different instructional models in 1 and 2, and I think it brings me to the point that it's a lot of coloring. It is. That I think the important takeaway is there's no one-size-fits-all instructional model that can be used for all math lessons. Whereas in primary reading, we've been using one dominant instructional model, which is I do, we do, you do, that gradual release. In early mathematics, that we have a number of different instructional models. It may be an exploration type activity, which is closer to the second one that you saw, where pupils develop new mathematical understandings by working through a problem and comparing their understandings with each other and with the tasks. We may have one that's more guided learning or guided practice, which is closer to the first one that you saw, which is a teacher-led discussion and question and answer. So I want to guide pupils to new and deeper understanding of a specific strategy that you can use for addition. I may have one where I'm using a mathematical model. Either children are using a mathematical model, I'm using one, we're developing one to show our understanding of an abstract concept. I may have a lesson which is just independent practice or application. And I may have an instructional model where I'm blending in elements of these within the lesson. So we don't have one instructional model that fits for all mathematics lessons. But we do have a place for direct and explicit instruction in mathematics. So regardless of the model, there is a place for that. So in the guided practice type or the teacher modeling type, we have strong teacher-led discussion component, and that's how children are coming to understanding is through that teacher-led discussion. In the exploration lessons, we have carefully structured teacher follow-up discussions. So I want to make sure that by the questions that I'm asking them, that I am bringing out what it is I wanted them to learn, and I'm making sure that that is solidified and deepened, that everybody comes away with the same understanding. And so the exploration lessons are very different than discovery learning. And Alfieri in 2011 did a meta-analysis of 164 different studies on discovery versus non-discovery type lessons. And unassisted discovery, where it's just open discovery, doesn't really benefit learners. So what we need is that we need to infuse those type of exploration lessons and with some explicit instruction, but implicit instruction that encourages pupils' mathematical reasoning, their justification, and their explanation skills. And that is critical in mathematics. Okay. So if you look at evidence-based reading and math models, some commonalities that in both of them, we need to acknowledge and respect developmental progressions. In both of them, we need to scaffold learning so that pupils are moving progressively towards deeper and stronger understandings. And both of them infuse elements of explicit teacher-directed or guided instruction. But in mathematics, we need to infuse it with mathematical problem solving, opportunities for them to develop mathematical processing skills and mathematical reasoning skills. And we need to develop deep and connected understanding. So I sometimes say that in mathematics, we spend a whole lot more time on critical thinking and what would be the equivalent of comprehension in reading. Okay, so I thought we might, I might end with a question for the other panelists before we open it up. And I guess for my colleagues, how do you see the research or evidence-based instructional strategies that you talked about in your presentation? How do they fit into the instructional models that we've described here?
So I'll jump in. I think something Louise said about the models that you showed, especially the second one where they're coloring in the patterns, about linking to the abstract, points to, I think fits with the idea that a lot of times letting the students explore with something that they're already familiar with and using that to build some idea about generalizability and how does this fit, you know, it can be really strong so that they're starting exploring with something they're familiar with, but then that activity, if the teacher scaffolds it correctly, allows them to actually see the linkage with something that's more generalizable, you know, a strategy or whatever that might be more generalizable. I also think about the use of games in school. I remember when I was a child, we used a lot of dice in school, though I think we had to call them number generating devices because dice, anyway. And that we were essentially playing games we might play at home, but the teacher was scaffolding to help us understand some mathematical principle or generalize or see a pattern through that very familiar game. So just a couple examples how that might fit.
And Norma, this is Leanne. I can jump in. I think you've already mentioned the importance of building on prior knowledge and thinking about the developmental sequence and how knowledge progresses over time. And as Wendy was just talking, one of the things we can think about too is how to use students' prior knowledge that we've identified along the developmental progression as a way of building on their students' exploration, and then deepen as we move into areas in which their students are still developing or emerging, their understanding is emerging, that we can then bring in more of a guided approach in instruction. So using kind of that developmental progression to think about how we can scaffold, as both of you have said, scaffold that learning pathway that is allowing exploration and allowing students to build on their prior knowledge and use that as a basis for their explanations and justifications, but then making sure that they're moving into the new learning with the appropriate amount of support.
Okay.
And yeah, this is Deepa. I just wanted to agree with what Wendy and Leanne have said, and definitely, you know, building on that prior knowledge and what students are familiar with and scaffolding that in the classroom.
Okay. Well, maybe I could just turn it over to the people who are still here and still listening. Any comments you have or concerns you have about instructional models for mathematics, either based on some of the ideas we've presented so far or maybe things we haven't brought up so far?
Sorry, this is Luis. It's not a concern, just a thing that popped into my head as I was listening to all this is that, you know, the difference between formal and informal is presented initially kind of as a binary thing, whereas I suspect it's more like a spectrum. And one thing that I really liked about Deepa's presentation is that it made me see how manipulables are kind of a step in the direction of formality because those are not concrete objects. I mean, sorry, those are not what to say. Those are not everyday objects. Those are kind of abstract objects because you're not playing with coins or with mangoes. You're playing with, you know, kind of a platonic object, if you will, a little square or a little circle or something. Is that a valid perception that there's kind of a spectrum there?
Wendy and Deepa, do you want to jump in?
Yeah, I saw your chat. There's a few chat questions. If we have time, we'll come back to. And I saw that. Yeah, that is true. That can be kind of a bridge to the more abstract with just symbols. I will say that manipulatives can be easily used badly. So they could become just as abstract as the symbols if they're not done properly. So the teacher really needs to scaffold that what you did with the actual mangoes is the same as what you're doing with these blocks. Like the teacher still has to scaffold that step, or the manipulative model could seem as abstract to them as anything else in formal mathematics. So I think that's true. It has very good potential for that, and that's a really good use of it. But it still has to be scaffolded and done well by the teacher.
Sure, got it.
Yeah.
Thanks.
Okay, well, I think we're going to move on to the second part, and we can come back to these questions at the end when we have an overall discussion. So the second part of this presentation was looking at sort of the type of professional development that might transition teachers to using these evidence-based methods in their classroom. And I wanted to start with a question, which is one I often ask primary teachers or math curriculum people. If you had a P2 pupil who said to you, why do we say that 7 is an odd number, but 8 is an even number? How would you respond with a P2 explanation of that? So I'll let you either put some ideas on the chat, or if you want to unmute and just, how would you do that? Okay. So we've got some ideas. You could divide 8 by 2 with no remainder, and that's true. Okay, that's a more abstract answer. Perhaps linking it to sharing. And the third one is you can divide 8 equally between 2 people. You can't divide 7 equally between 2 people. I think you've got some really good ideas here. And what always strikes me when I ask this question is what I get is a very abstract explanation. The idea that maybe it's sharing and there's nothing left over when you share is not something that people come up with easily. And so what I wanted to talk about in this presentation is that there's 2 types of knowledge that teachers need in order to be really effective early primary math teachers. They need pedagogical content knowledge, which is what we've been talking about so far. So how mathematics is structured as a discipline, what are the developmental progressions, what are the evidence-based instructional strategies, and why are they important? But they also need what we call mathematical content knowledge, which is understanding math concepts and procedures and being able to explain them clearly. For example, does multiplying always result in a bigger number, and why not? And if, for example, if 7 is bigger than 3, then why do we say that 1/7 is smaller than 1/3? So teachers need to be able to have a deep understanding of these concepts and be able to explain them in a number of different ways, including in a very concrete way. So I'm going to focus more on number 2, the mathematical content knowledge in this presentation, because the pedagogical content knowledge is what we generally address when we're doing workshops with teachers. So why is it critical to getting them to adopt these new instructional practices? And one of my favorite quotes is one of Deborah Ball's, where she says that teachers can't help children learn things that teachers themselves do not understand. So if I don't understand it, I can't explain it. And if I can't explain it, I'm probably not going to use those open-ended questions because I'm not sure how I'm going to be able to respond to them, which is probably why teachers' content knowledge has a bearing on how they teach and on what pupils learn. And the stronger and the more extensive teachers' content knowledge, the better their pupils perform on assessments. And so how do we develop the content knowledge? Well, there's lots of research saying one way is to immerse teachers in authentic problem-solving experiences. So have them actually solve a really rich primary math problem that includes some understandings that they may not actually have, and then have them deconstruct what they learned, how they learned, what that says about mathematics, what is mathematics, and what that says about how mathematics should be experienced in the classroom. I think some of you attended a presentation I did previously looking at sort of the results of a numeracy pilot that we did in Ghana, and this was one that was led by School to School. And it had a number of components, including workshops on pedagogical content knowledge, but it also had weekly sessions which started with the teachers engaging in an authentic math problem and then deconstructing it. Or we had them watch videos of teachers solving math problems. And I'm going to give you some examples of the ones that we did. So we would do, if they were going to do, just before they taught place value, we had the teachers work with a partner to solve the problem that's on the left in blue. So thinking of a 2-digit number, then the digits add up to 7. What might the number be? What might the largest number be? What would be the smallest and why? What would be the largest if we didn't include 0, and so on. And that would be followed by what is more a pedagogical question, in which Kobe has 23 counters. His teacher asked him to show how many counters represent the 3 and 3, and he holds up 3. Then the teacher asked him to show how many counters represent the 2 and 23, and Kobe holds up 2 counters. And then we would ask the teachers to work through the problem of, is he correct? And why or why not? And so what we're trying to do is to go from what we hoped was the pedagogical knowledge that developed in blue to looking at how do we use our understanding to teach effectively in the classroom using accurate models in the classroom. Another example that we gave them was, this is Johnson. He's asked to calculate 35 minus 19. So what he does, he adds 1 to each. And he says, well, 36 minus 20 is a whole lot easier. So if 36 minus 20 is 16, then 35 minus 19 is 16. And so we would ask them, does this strategy work? And why does it work or why doesn't it work? And how would you explain this strategy to a P2 or a P3 child? And then if you added the same to each number, would it change the answer? So instead of subtracting 32 minus 11, you were to subtract, and you get the question of 31 minus 10, does it give you the same answer? And so are these strategies working, or why not? To identify the good problems, we started with a collection that Deborah Ball put together and have been released. So any of you are interested, you can check that. So that was our starting point for creating really, really effective problems for teachers. What surprised us at the end is when we did an anonymous survey with teachers to find out what are the activities that had contributed the most to their understanding of how to teach mathematics. And number one were the workshops that we did on pedagogical content knowledge and effective strategies and so on. But number two was working through the problems. And that's how they figured out how to do this in the classroom. The videos were not as powerful, and maybe because our videos were not that great, but definitely watching the videos was nowhere near as powerful. And we looked at the results of an impact evaluation. Now I can't attribute this to the problem solving, but the pupils in our treatment schools significantly outperformed after only 1 year, but it was actually 6 to 8 months, the pupils in the control schools. So that was 3 to 5 percentage points higher on the traditional tasks and 17 to 18% higher on conceptual understanding, and no difference with respect to gender, and only minimal differences by locality or SES. Okay. So I'm going to end it there, and we're going to open it up to any questions you have about the entire presentation, or if you want to discuss some of the cross-cutting issues that we didn't get a chance to address during the presentation.
I will say there were 2 previous messages that were asked through chat, questions.
All right.
One was about teacher-made material. In relation to manipulatives, especially base 10 blocks, the question was opinions about providing these materials to teachers, which is expensive, versus teachers making them themselves. So of course, then some teachers might not do it, etc.
Yeah.
And then the other question was about where do where does kinesthetic learning come in, like movement?
Yeah. Okay.
So, and that's not just for you, Norma, that was sort of any time during the session. So anybody who wants to answer those.
I mean, I'd like to talk about the teacher developed versus distributing. And I think it depends on the concept. Like there are some concepts that you can teach very easily through locally available materials, like counting. Everybody has counters, whether they're bottle tops or whether they're twigs or whatever. So anytime that you can actually accurately represent the concept using locally available materials, that would be my preferred route. And the most success I've had in doing that is when we don't get the teachers to collect the materials, but we tell the parents ahead of time, for this semester, your child must come with a bag of X number of bottle tops. And so the kids have their little bags of counters in their desk and they can take them out at any time. So that takes the whole management of the resources away from the teacher, and it makes the kids responsible for having those materials and ready to use in class. That said, there are some concepts that are really hard to represent through locally made materials. For example, if you look at geometric shapes and the relationships between them, attribute blocks, for example, unless they're really accurately cut, you don't see the relationships or the pattern blocks. The pattern blocks. So I find that those ones are really hard to make. Base 10 blocks are notoriously difficult to make, which is why we generally use bundles of twigs or bundles of sticks. And that works well with 10s, but a bundle of 100 is huge. That's sort of my perspective. If you can use the local materials, use them, but some concepts are really hard to represent accurately with local materials. Anybody else?
Yeah, I just wanted to agree with you, Norma. And definitely, I probably should have said this also in my presentation that, using objects that are familiar to students is definitely, it's very helpful, because then, if they see bottle tops, they do see bottle tops at home, and they, like you said, Norma, bring it to the class. They're bottle tops that they use as counters. So they understand it's not like a foreign or an object or that's given to them in the classroom that only stays in the classroom, but something that's in their environment. And also, and you're right in terms of, the bundles are really great, but then they do have a very limited, use, in the sense that they're great for the 10s place, but then when you get to the 100s, then I think Wendy's also, and Leanne has mentioned this as well, is that scaffolding process is really important, kind of bridging that, okay, we're using the sticks or the twigs right now, but then we're going to be representing this into 100. This is how 100 block looks. So I just wanted to add to that and agree with you.
But I think one of the advantages of the kind of industrial or standardized manipulables is that they are one step in the direction of being more abstract. So, yeah. Maybe, I don't know. You guys, I'm not an expert on this stuff. You see what I mean? So, yeah.
I mean, I saw a comment previously from Ben about how much he loves base 10 blocks. And, if I only had money to buy one commercial material and distribute it, it would be a way of finding them to get base 10 blocks, simply because you can do so much more with base 10 blocks. When you get to P3, P4, P5, when you get to multiplication and division, then you can with bundles. Yeah.
I have a much more general question here, but if people have specific ones, that would be better, because I don't want to take up time with generalities.
Did we want to get to the kinesthetic?
Oh. Okay.
Oh, that I would be very curious about.
I'll just jump in. I mean, there are a number of exercises I've seen of actually physical models, for example, moving in the classroom on a, where a teacher puts like a number line on the floor, and the students actually walk through a problem on the number line on the floor. It's a really nice way to think about addition, subtraction, as well as negative and positive numbers, which can be represented through which way you're facing. I don't have a general answer, but you know, I know of specific examples of ways that representation can be through physical movement.
Okay.
I don't know if others have other.
Yeah, and I think even when you're teaching, you know, the numerals and how before they start picking up a pencil and trying to make a 2, doing it so that they're making it with their body or making it with their hand, their figure in the air. I think that is all, or making it in the sand, to transition them to picking up a pencil and actually recreating that shape. I think that's important. It's important when you're introducing statistics that we start by making graphs that are made with the children themselves before we transition to representing these, you know, a little bit more abstract with pictograms or with objects.
Got it.
Oh, and I see we have another question from Lisa saying, what might be the place for parents or families to help? Anyone want to try that one?
This is Leanne. I can jump in.
Yeah,
so I think one of the key aspects of parents or families engaging with mathematics is really helping to bridge some of that formal and informal, but then also increasing just the exposure of students or children to mathematics. We're taught as parents when our children are extremely young, the value and importance of reading and pointing out describing sounds of words, but we're not often encouraged and taught how to think about talking with our children about numbers. And in some of the work that we've done, and others I know on the call, in looking at how to support parents and families in early mathematics, is really working with parents to see how, for them, how they use mathematics in everyday life and how they engage with mathematics in so many aspects of their daily living, but also bringing mathematics words into the conversation. So in something where they may be using mathematics in their head, even if it's something as simple as counting out the number of utensils needed for the number of people, those are things that parents can do and can overtly make their mathematics heard by children and known by children, but also playing games, using puzzles, using so blocks at home and building. There's a good amount of research that references the value of block play in students' spatial development and spatial reasoning. There's, I think, a number of ways in which we can use games and play at home to bring in our mathematics language and mathematics concepts so early as well. So others I know, Deepa, if you wanted to jump into.
Yeah, no, exactly. I agree with you, Leanne. And I just wanted to add that, you know, just also bridging the kinesthetic aspect, you know, like simple games that we play outside of school, like hopscotch or like jump rope. So like counting by ones and then counting by twos when you're jumping on a jump rope, for example. Things like that, you know, they're informal, but they reinforce a lot of the number counting and recognition of numbers. And just as an example from India, we play the game Carom a lot. Some of you are familiar, but even you know, when children are playing Carom, it's like how many of the, you know, there's kind of an ivory color as well as black color pawns, and so how many of each are you getting and counting that, and then counting it in twos or counting it in threes. So those type of games are also fun for children at home.
Thank you.
So you'll all see on the screen that I've shared a website where you can also download the document that we shared. So this is the ShareEd website from RTI International. And so the instructional strategies for mathematics is listed here. There's the link that I originally shared to the Global Reading Network, and then you can download directly from here as well. So just for those of you who need to drop off the call, I wanted to make sure you knew where some resources might be available.
And we'll be looking for how to get the recording and PowerPoints up through CIS, but I'll also make sure that those things are also posted on the ShareEd site. So that would be one place people could go to get the PowerPoints.
Do we have time for a slightly less specific question, a little bit more general? Or, I mean, I can do it offline with Wendy too. Or are we up to? I don't know what our time limit is.
The session does not automatically end, so anybody who can stay can stay.
Okay.
As long as Leanne can stay, because she's the host.
Yes, absolutely. We just want to
questions?
thank everybody who was able to join us for the session, and we apologize for that initial disruption, but thank you all very much for coming, and anyone who needs to drop off, again, we'll try to make these materials and resources available.
So I had two questions, or, well, I guess one is more of a suggestion. And the suggestion is, as Wendy, you may remember that the Gates Foundation drafted myself and Ben to help them think about next steps in their research and funding, or funding of research. And just a reminder I mean, this guide here that we've been, that just got shared, has been shared with them. And of course, Ben is going to be doing some stuff with them, as well as myself. But just make sure you stay tuned to that, because I think it'd be a great way to get some of these insights injected into, what we already know, and therefore what we still don't know, kind of stuff. The other, so that's just the comment. The other is more of a question, and that is, you kind of started out with an explanation of why informal math might not be enough. And my guess is that the reason you guys feel a need to even say that is that maybe in the past there were some debates around whether, math, math instruction is not that hard. Kids pick it up informally anyway. So what's all the hullabaloo about, making it formal and so abstract, and, let's just let the kids be kids and pick it up on their own. And so I guess it's a two-part question. A, am I correct in perceiving that at some point there were people running around saying that? And B, has that debate now been pretty much resolved, and people understand the value of both types of mathematics?
So I would
so
say,
this is, sorry, Wendy. Oh, okay, just really quickly, Luis, and I agree that, maybe there's a misunderstanding or misconception around that, because when we do say that children have an innate understanding of mathematics, and, maybe they could perhaps even learn, simple multiplication and division on their own, but there also is like neuroscience research that supports saying that children don't develop a mental number line, which is really important.
Yeah.
For advanced addition and subtraction without formal education. So I think
no, I get that part. I guess my question is, out there in the field, or are there people in the ministries, for instance, or even in academia in some of the developing countries, that have this notion that you can be completely natural and completely informally based with regard to mathematics, and that there's no need to formalize it? Is there anyone who thinks that way?
Yeah,
Louise, I would say the problem is almost the opposite. I think a lot of people see school math, like see math as something that's really abstract, and don't see how it's connected to every day. And so when you're trying to use math to solve problems, which real life problems, which is supposed to be what math, a lot of what math is for, that link is missing, because and that's another reason, like for me, why the language aspect is really important, because a lot of people see math as language free because it's just numbers. But in fact, developing a conceptual understanding depends a lot on language and understanding. And so, I think it tends to be the opposite, almost, aside from those people who are really into discovery learning and you know, constructivist, but that's a small group. I think most people just see math
because
as only
in
something
reading,
abstract.
I mean, in reading, to say, well, reading can be learned naturally, just the way language is learned naturally, verbal language is learned naturally. I mean, even that is not quite true, but yeah, okay, I got it.
And Wendy, you were talking about how, in one of our previous discussions, about how math is like reading comprehension.
Yeah, I like to tell people that math is like the comprehension part of reading. Like there are a few things, yes, you can learn by sort of, I mean, the way that, for example, when you learn phonics, it's fairly, part of the reason that the I do, we do, you do model works with a lot of reading is the basic elements, in some ways are mimicry that you can do really well through I do, we do, you do. And it's when you move into the more of the deeper comprehension that starts to get lost. Whereas math, that's where you're starting, because if you don't develop, if you just learn a bunch of procedural skills, you're gonna be like a lot of Americans who say, I can't do math, and they can't figure out how much they get off if the store has a 50% sale, you know? So yeah, I often say that, you know, teaching math is like teaching the comprehension part of reading.
I just wanted to follow up. Luis, you mentioned that looking at sort of a research agenda with the Gates Foundation. There's another publication that we did, that comprehensive math and literacy programs, and there is a chapter on that, on sort of what are, where do we need to know, what are the gaps in our understanding in the research agenda, and that was probably the chapter that had the least USAID editing in it, and so it's much closer to what it was we were trying to get at. So I think that's a pretty good starting point.
Well, just make sure that gets shared with Ben, because I'm helping Gates with, obviously as an economist, not the teaching and learning bit, but the systems bit, whereas Ben is helping them with the teaching and learning bit.
Okay.
Well,
hey, Wendy, this is Tim. I've got a question for you.
Sure.
So thanks for your guys' presentation. It was really cool, very interesting. I think the first thing that my gut reaction as soon as you finished was, oh my God, that's a lot of sophisticated thinking and planning around lesson delivery for one 6-minute instructional segment. Yeah.
Yes.
And how many instructional segments does a teacher have in a day, of, you know, if we're breaking them up into 6-minute increments or whatever, right? Which I recognize I'm sort of making this sort of like artificial, but I think we recognize that there's layers of complexity and sophistication behind a lot of the stuff that winds up looking pretty simple. But I don't know, like, I don't know that I have a specific question other than that was like my emotional reaction right off the bat. And like, I'm curious how you guys, you know, as the experts who care about our getting this right, would kind of like react to that and its implications for how we design like math interventions out in the real world.
Yeah, so I think that's a really good question, Tim, and to me connects to the whole thing about the thing about the Gates Foundation and what is the next area of research. To me, it's about how do you build this among teachers, and I think Norma showed a great example of some of the ways that they're trying to do this, and see some itching forward, so some moving forward. I would say again, the parallel with comprehension, like we've become better and better at getting kids to raise their ORF scores to read more per minute or whatever, but how much are we able to push the envelope on the comprehension? That's, I think, still an open question, and that's probably partly because it's harder to do. Like, you need the teachers to develop skills that are a bit higher level than what they may need to do in order to just get the decoding down. I think it's going to be much harder to find very simple routines that if you just get all teachers doing these simple routines, you're going to see big gains in the conceptual part. You might see some procedural improvements, but that's not going to get us far enough. So it is something that's hard to do, and I think that is definitely a rich area for research in terms of what are ways that we can be doing that better with teachers.
So I guess real quick, in case this changes your answer, but maybe it doesn't. I just realized what you were saying right there sounded to me like you were thinking my question like had the child as the unit of analysis in terms of the sophistication, but
No, the teacher.
The teacher, okay.
Yeah,
right.
the teacher. And I don't know if Norma has been doing this in Ghana. I don't know, Norma, if you want to add on any reflections.
Great to hear your voice again, Norma. It's been a long time since we are.
It's been a long time, Tim. In Ghana, we had a really, really limited budget. So all we could work with was the teachers. So we couldn't build any student materials or do anything like that. So we were really limited in how we could go about changing teacher practices or the supports that we could give them to change their practices. I do think that the questions that you're raising is a really important one, Tim, because there's a level of knowledge and understanding that you need in order to develop those really simple math activities, but simple activities that build deep understandings. We could end up with simple activities that build very superficial understandings, in which case we're no further ahead than with what teachers are doing right now. So I do think that we are going to have to invest a lot in professional development for the people who are going to be supporting trying to develop these programs in country. I'm working with one country right now where all of the people working giving technical support to the numeracy are reading specialists. And it's really, really difficult to help them understand why what they're proposing is not going to get them where they need to be. Yeah, I think it's a really, really big question. How do we make it simple enough for the teachers, but simple activities that build really, really rich and deep understandings? And I think there is a level of technical knowledge that you need in order to be able to do that.
Thanks for that. I think just one last quick sort of bit of feedback on that first presentation. I loved the discussion of the sort of progression, the developmental progressions as like a framework for thinking about differentiated instruction. Largely because I think I have, having largely tried and failed myself as a teacher to differentiate instruction and having read about attempts to differentiate instruction that have failed, I found that to be a useful mental construct, certainly better than what I had in mind before about how to do it. I still don't know that I'm clear on how to like effectively differentiate that, but I guess, this is not the place for you guys to tell me how to do that, but I'll be interested if you guys have great resources about how that gets done practically in the real world. I would love to, maybe skim over those if Wendy can share them.
Yes, we can certainly put some resources together and add those to the PowerPoint presentations. I think if you're looking at some of the differentiation frameworks like Tomlinson's, they talk briefly about like differentiating content, and then there's differentiating process and product. And I think the hard part is differentiating the content. And we've also heard, or how to, where we see so little guidance in some of the literature. And some of the strategies that we've talked about in this presentation, I think are really useful in differentiating the presentation of the materials. So whether you're bringing in different manipulatives or you're bringing in different representations or models, so moving towards more abstract for students who are developing more sophisticated understanding, continuing to keep the representations, but maybe moving away from some of those concrete manipulatives, moving more into number lines, and then connecting that to the abstract representations would be a way of differentiating along the representation. But thinking about how to differentiate the content is really where some of those, the learning progressions or the developmental progressions can help think about where the students, how to cluster students based on their understanding, and then how to tie those with some of the differences in presentations and products that are also strategies for differentiating.
Can I comment, or kind of a half comment, half question on this? because I was also had exactly the same worry as Tim. And I think there is a difference, though, between mathematics and reading, which you can check me on and tell me I'm completely off base. And that is that in reading, if there's a skill that you're trying to, that has to be mastered, and you bewilder the teacher with too many choices and therefore they don't do it well, then that really hurts. Whereas I have a feeling that many of the things that were presented today were alternative approaches to, I don't know how to put it, but it's not, if you don't do some of the stuff Deepa was saying, for instance, it's not going to kind of damage the kid or leave. These are kind of, I don't know what I'm trying to say. It's something along the lines of, there is kind of a less, I don't know what I'm trying to say, but I think something around the fact that none of these things are kind of a do or die thing. They're just kind of different ways of approaching a similar skill. I don't know.
I think you're right, and I'm hoping that I'm coming through. But I think there's some challenges with the structure of the way in which
I agree with that. I'm just saying different ways of doing the mathematical models. Like if you give the teachers a lot of choice there, and they give it, oh well, no, sorry, you're right. Yeah.
Yeah, you want to give them an accurate one, and things that they can show with the materials they have at hand. You don't need to give them 5 models. Give them one really accurate one.
Okay, that's so I guess in a sense, I mean that answers Tim's question, I think, to some degree. But I think that's, figuring out what sort of the optimal one is under the conditions that teachers operate in the developing world. They're tired, they're hungry, it's hot. Figuring that out might be a worthwhile bit of research, and trying different things out in the field. I mean, remember Ben's initial primer, had something like, I don't know, 6 treatment arms or something. So, and he figured out a lot of stuff by doing that, but it wasn't cheap.
Yeah, I would agree. I'm thinking in Madagascar, the discussions I had with them, because the context varies so greatly from one end of the island to the other, that their starting point was they would suggest, for example, counters. What you would suggest for counters would vary from one region of the country to the other because they have different natural resources available to them. So I think you have to find one that is accurate and available in the locality, but as you say, there may be some level of sophistication to figuring out what is available in different localities and do these all work the exact same way. Counting is a little bit easier, but when you get to things like representing groups of 10, how you would do that and what that would mean, how you would use that physical model in the classroom may be different.
Yeah.
Deepa, have you had experiences with that in the different contexts you've worked in?
Yeah, I think it's similar. I think, definitely counting to 10 and then creating those bundles it's much more straightforward, but then really kind of bridging that to understanding what 100 means, things like that. It's similar to that. And it just depends on what the child is familiar with in the context. Some kids maybe haven't even seen straws. So even understanding that, why we're using straws to make those bundles needs to be explained.
I see we have a question in the chat room about whether when the teachers were doing the problems, did they have to discuss amongst themselves as to how they solved the problem? And if there were different ways of solving problems, that would allow them to see that children might give children different ways of solving. That was an essential part of the problem solving, that teachers could see that the way they solved it was not the same way as that pair sitting next to them, and that both of them were valid, and why you might want to encourage that in the classroom. So I just wanted to answer that was an essential part of the problem solving. I think Leanne says she's having some problems with her audio, so I will just put it out there. Is there anything else people would like to discuss or just chat about?
Not really. This is Luis. This has been really, really a good start to the day.
Okay, Wendy and Deepa, anything else you would like to?
No, just again, thank you everybody for your patience and figuring out how to make the Zoom thing work, and for all your participation and contribution.
Yes, same thing from my side too. Thank you everybody for joining and for your patience. It's been great to have this conversation.
Thank you.
Thank you all.
Thank
Bye-bye.
you. Bye.
Bye-bye.
Have a good rest of your day.
Bye.
Bye-bye.
Bye-bye.
Bye.